Dear participants, welcome to the technical section number 4 of TTMD Symposium. In this session, we will have 3 speakers who will talk about the general topic of novel HVAC system design approach. The first of these speakers is Mr. Kroeger. The title of his presentation is From Data to Impact: Exposing the Reality of Refrigeration Performance Discrepancies. Mr. Kroeger, would you please introduce yourself? The floor is yours. Thank you.
Thank you very much. Yes, underperformance in refrigeration, a technical challenge. My name is Tim Kroeger. I am working as Business Development Manager for Eurovent certification. I am German. I'm a German native speaker located in Hamburg, in the northern part of Germany. And this brings me to my first point, because Eurovent certification, or Eurovent certification, whilst headquartered in Paris, France, is a truly international company. We speak about 20 different languages. We have offices in the UK, in Poland, in Ireland, and now in Germany as well. Eurovent certification is an independent certification body with programs for 44 different product groups ranging throughout the whole HVAC&R range. In the air conditioning and ventilation area, we are quite strong, with about 60% of all products sold in Europe being Eurovent certified. But for refrigeration, particularly in Northern Europe, including the German-speaking markets, we will have to increase our efforts. Now, what does underperformance actually mean? Change my slide because I see the panel. Yeah, that'll do. We speak of underperformance whenever actual performance figures deviate from what is published or declared by the manufacturers. And please note that I refer to performance in general and not only capacity, because performance can include things like air volume, sound level, vibration, and so on. So when we have a deviation, a negative deviation of actual compared to declared performance, the impacts include a lower than expected energy efficiency with an impact on CO2 footprint. And for heat exchanger in particular, and I have a little case study later on, it means a suboptimal heat transfer. And in the worst case scenario, insufficient cooling capacity as compared to specifications by the planner. If refrigeration or air conditioning equipment has to work harder constantly because of, for instance, a lack of performance, or in this case, capacity of the heat rejection equipment, we can assume an accelerated degradation of the equipment with increased maintenance efforts. Now, usually what specifiers, and that means consulting engineers or technical managers of large end users such as supermarket chains, they can only specify their equipment based on declared or published data by the manufacturers. So once again, if we have an underperforming system, we have an higher energy consumption. That pretty much goes without saying. Mentioned maintenance overloads. In terms of the CapEx, we have a little bit of a false economy, because obviously if manufacturers over-declare their performances and under-deliver them, typically they offer their equipment well below market price, or compared to other manufacturers who are certified and whose capacity ratings are verified. It certainly has an impact on the operational expenditure, and this can be very, very significant, as we will see in a later case study. Worst case scenario, if the system doesn't perform to specifications at all, think about a cold storage facility, for instance, where product temperatures during storage are not maintained. It could lead to very, very costly retrofitting following a system failure. So with that being said, well, maybe before I do that, certification is much more than just simple labeling based on self-declaration. You see that with the CE marking. It's pure self-declaration by the manufacturer. You see that with some of the German labels that are based on sustainability statements of the manufacturers. Certification is a very involved process that includes but is not limited to physical testing of equipment. And once the manufacturer goes successfully through that process, they can very proudly bear the Eurovent certified performance mark on their product. Anyways, coming to the case study, we have actually done a datasheet analysis of non-certified CO2 gas coolers. I would like to state at this point in time, the only reason why we chose CO2 gas coolers is that on the heat rejection side, and it's still seen as a relatively new technology with a little bit of uncertainty in regards to, for instance, correction factors. This does not in any way, shape, or form mean that we do not support CO2 as a refrigerant. Personally, I'm an industrial refrigeration person. So I've grown up with ammonia as a refrigerant, and during 20 years of work with the Danish manufacturer Danfoss, CO2 has always been the future refrigerant for supermarket food retail installation. So we totally support what is commonly known as natural refrigerants with a very low GWP. So CO2 as a refrigerant, just a little bit of a recap. Some people say it's a bit of a weird refrigerant with special thermodynamic properties. As a matter of fact, the pressure enthalpy diagram here on the lower side of the slide is exactly the same as any other refrigerant. The principal shape of isothermals, for instance, is exactly the same. The only difference being is that for typical summer temperatures, even in Northern Europe, we operate in the so-called transcritical process. And that is because CO2 has a relatively low critical point. What exactly is the critical point? I would encourage you to Google the words Danfoss and CO2 properties, and you will immediately find a very useful teaching video that's now, I would say at least 25 years old, but it shows a vessel with a sight glass where you actually see what is happening at the critical point. Beyond the critical point, the density of the vapor is exactly the same as the density of the liquid. Hence, there is no separation of liquid and vapor as in the wet vapor area, and it becomes kind of like some stuff, like a plasma-like substance. One of the aspects of CO2 is that under certain conditions, an increase in CO2 gas cooler pressure. This is why, by the way, why we call it a gas cooler and not a condenser, because we do not condense vapor into liquid. We cool a gas above the critical point. Under certain circumstances, an increase in the gas cooler pressure might lead to an increase in COP. This is a completely different subject. What we would like to do is we would like to analyze the thermodynamics during the heat rejection. The first example is heat rejection at 90 bar gas cooler pressure, which corresponds to the SC20 standard conditions. And what do these different colors bars represent? Well, the green bar represents the first part of the heat rejection process. By the way, that limit between green and red is completely arbitrary. The green bar represents heat transfer at a relatively high temperature differential. As you can see here, we cool the CO2 down from 110 degree down to about 40 degree. And then the red bar represents a reduction in enthalpy, a heat rejection at a relatively low temperature differential, here from 40 degree to 35 degree. So once again, this sort of the differentiation between green and red is completely arbitrary, but we have 85% at a high temperature differential, and 15% at a low temperature differential. If at the same ambient temperature and the same CO2 gas inlet temperature, we reduce the gas cooler pressure, we have this picture, and all of a sudden 37%, more than a third of the capacity is transferred as a relatively low temperature differential. What does that actually mean? And it took me a day to wrap my head around that, even though I had dealt with CO2 during my time with Danfoss for more than 20 years. Well, heat transfer, I try to describe it in a sort of common language way. Heat transfer at a low temperature differential requires a higher surface. It eats up a lot of surface. In that respect, it's a little bit comparable to creating superheat in an evaporator. As the gas superheats and the temperature differential between ambient and evaporating or refrigerant temperature decreases, it eats up a lot of surface area of the heat exchanger. So as a matter of fact, when we move away from these standard conditions SC20 to lower gas cooler and lower gas inlet pressure values, we need to apply correction factors. At this stage, I would like to say a couple of words about how the certification is governed. Certification follows the so-called technical certification rules. That is a Eurovent certification document. But these rules are in turn decided upon by the program committee. And in the program committee are not only members of Eurovent thermodynamic experts, but also very technically competent representatives of participating manufacturers. So when we come up with, as a team, come up with these rules, they really represent industry consensus. So it is an extremely transparent process. I'm just showing this to show you that as you move away from standard conditions, you would have to apply certain correction factors. So what we have done now, we have actually looked at the certified capacities and the non-certified capacities. And as we can see, the non-certified capacities, where that red big arrow points towards, they typically do not apply significant enough correction factors. And we thought this is very odd. So what we've done, we've analyzed 48 different products, non-certified products. And when we used published data to determine capacities at conditions different from the standard conditions, we found deviations in 100% of analyzed products. And the deviation ran from the lowest deviation, which was 12%, to the highest deviation, which was 31%. Now, one thing to remember is that we simply analyzed published data. And this average deviation of 23% is actually based on the assumption that the published data for the standard conditions by the manufacturer is accurate and correct. Now, I'm not saying that all non-certified manufacturers over-declare their products, but even with that in mind, and only using published performance data, we have a deviation as soon as we move away from the standard conditions. A very careful eye on the time here. What does it actually mean for a typical refrigeration application? I have actually shown a supermarket simply because if we look at Northern Europe, and in particular CO2 gas cooling, then the supermarket industry is probably one of the largest users. This is just a system that we have analyzed and simulated. As you can see here, this is the typical medium temperature and low temperature split, 250 kilowatts on the medium temperature, 100 kilowatts refrigeration capacity on the low side. So this is a big consumer market in Germany, one of these big supermarkets of, let's say, 3,000 to 5,000 square meters. As you can see here, we have other design parameters, ambient temperature, and so forth. Electricity, the specific cost of electricity in Northern Europe, in particular Germany, is actually quite high. I don't think you have the same number in Turkey, but for Germany, for new contracts, particularly after the events of the last year and with what's happening in Ukraine, if you plan a new supermarket, then that's pretty much what you have to calculate with. Anyways, I'm going to go through these slides relatively quickly because they just show the performance of the system at different ambient temperatures. In essence, this is only one figure that is of interest here, and this is the total electricity cost per year when you take into consideration the gas cooler fans as well as the compressor electricity cost, being the main contributor to the cooling cost in terms of OPEX, operational expenditure of a supermarket. Two things, when we run up the system with rising ambient temperature, first, in order to maintain a certain system temperature, the fans have to work harder, they have to run faster, and from a certain point onwards, the system temperature sort of starts running away a little bit, and from that point, the feeds are running at full speeds, all of them, and the compressor has to work harder. That is what this figure on the lower right is based on. If we compare that to a system with a CO2 gas cooler with this average 23% lower capacity, well, in this slide, it's called an oversizing coefficient. That's a bit awkward terminology. But as we saw from previous slides, we have an average of 23% deviation. Then that's the figure. In comparison, there is a lot of text on this slide, but there's for an operator, there's only one figure that's interesting, and that's what is it actually costing me per year when a system or a heat rejection system CO2 gas cooler underperforms by 23%, and that is almost 20,000 euro per year. Obviously, these systems operate over a minimum of 10 years in their lifespan. Typical refurbishment period for like a German supermarket is a little bit longer, maybe 12 years. For some of the low-cost retailers, up to 15 years, but that's rather rare. So we have a minimum of 190,000 euro. And this is why I said the CapEx consideration is a very, very limited and wrong economical consideration, in my opinion. If we look at the CO2 print reduction that we can achieve if we use certified heat rejection equipment, for an average supermarket, this is about 25 tons per year. And this is only for the CO2 gas cooling. We haven't even started to look at the cooling cabinets, the display cabinets in the supermarkets. We call them RDCs, as in refrigerated display cabinets. But I have conducted an initial study, and we estimate that we can at least save twice that amount when we start looking at the performance of these, particularly these open display cabinets and the energy classes there. So that means for the entire food retail sector, that's the totality of all supermarkets in Germany, simply by using certified heat rejection equipment and certified refrigeration equipment in general, we can save up to 3 million tons of CO2 per year. Now, this is just a figure, and I can't wrap my head around what does it actually mean or what does it compare to. Just checking the time. No, we're running pretty good. We're running pretty much on time. I have looked at some other measures. For instance, my hometown of Germany, about 10 years ago, they have made a decision to purchase only eco-friendly electricity, that's renewable energy, for all of their public transport. Now, Hamburg is it's one of the biggest cities in Germany with about 4 million people living there. I don't know about Turkey. It's probably a medium-sized city or larger city for Turkey. And I don't know exactly what eco-friendly energy entails, but they probably plant a tree for every 1,000 kilowatt hours consumed, or they purchase energy, including CO2 credits. The percentage of renewable energy is actually quite high in Germany, and the rest we get from France based on nuclear energy with very little CO2 footprint. And this measure, all of Hamburg public transport on renewable energy has saved about 1 million tons of CO2 over the last 10 years. Now, taking into consideration the last slide that I show you, we can do triple that amount in only 1 year for the food retail industry if we use certified products. That is a lot of CO2 footprint reduction, and decarbonization is in everyone's mind these days. As a matter of fact, most food retailers now, even the low-cost food retailers in Germany, have included decarbonization in their mission statements. So not only the Rewes or Edekas of Germany, but also the Aldis and Lidl, the really low-cost discounters, have included decarbonization in their mission statement. Now, I was actually quite surprised to see that whilst the turnover of a typical food retailer chain is very, very high, it's in the billions of euro, their bottom line is quite low, between 0.8, 1.2, 1.5% of their total turnover. The EBITDA is actually higher, but because of a lot of debt and amortization, the net result of a company like Rewe, for instance, is only about 700 million euro compared to 900 million euro that they pay only in interest per year. And then I have looked at the energy consumed per square meter, and that includes, of course, everything from lighting, heating, ventilation, and refrigeration. But it's approximately 4% of the turnover, particularly if we consider an expected 33% rise in energy following the events in Ukraine over the last couple of years. The general consensus is that refrigeration accounts for about 40 to 50% of the energy cost. So if we can, and simulation has actually proven that, particularly taking into consideration a half or one energy class reduction in the refrigerated display cabinets, we could achieve 15 to 20% reduction for the cooling energy consumption. And that would immediately increase the bottom line of the large food retailers in Germany by 50%. So in my opinion, that's fantastic. And I've actually calculated that. For instance, if Rewe, which is the largest independent supermarket chain in Germany, were to simply include the requirement for certification and capacity verification, therefore, if they were to include that in their refrigeration specification, we could hand them between 120 and 160 million euro per year on a silver platter. So, I'm not going to read through all that text. I don't like slides with a lot of text, but as you can see on the left-hand side, there's different aspects of the operation of a refrigeration system. And the further you go to the right, from simply in-house laboratory testing by the manufacturer to independent laboratory testing to a full product certification, only product certification ticks all the right boxes. For instance, when we look at selection software checks are part of our certification process. So we want to make sure that if a planner or a consulting engineer is using a manufacturer's software to analyze the performance at certain conditions, that then includes consideration of, for instance, these correction factors that I mentioned earlier. So for the manufacturer, they can use certification as a great differentiator in the market. And for the end user or the technical decider for any refrigeration or air conditioning application, they can have the peace of mind that what they select will actually perform to specification in real life. Now, I would like to invite you to download a white paper. I've included a QR code here in the presentation, which I'm pretty sure will be available on the website for the event. And it's available in, as a matter of fact, as we speak, it's being translated into Turkish. It's not quite available yet, but it's available in 6 or 7 different languages, including English, German, French, Italian, and soon Turkish as well. Polish is also one of the languages that's included. So with that, I would like to thank you for your attention. We're 4 minutes ahead of the initially scheduled time, so we're doing all right. And I will open the floor to any questions that you might have.
Thank you very much, Mr. Kroeger. I thank you for your impunctuality. So you were ahead of your time.
That is said to be a German
thing.
thing.
Okay, well, your presentation, your very informative presentation stated that the importance, or showed us the importance of certification, product certification, in our quest for a more sustainable future. So I'm afraid there are no questions from our chat box. But
that's perfectly all right.
Yeah.
I had a question that was asked to me during the recent Chilventa presentation press conference.
Please go ahead. Ask. Please read.
One question was, in fact, whether we as Eurovent support CO2, and that's why I included my comment earlier in the presentation. We only choose CO2 as an example because, quite frankly, for me personally, it's not a new technology, and CO2 has been around for many years. But on the heat rejection side, there is still a little bit of uncertainty as to how to derate the capacity at conditions that differ from the standard conditions. The other question that I was asked, and this is actually probably more important, someone said to me, Tim, can you estimate the percentage of non-certified products that underperform? And this is impossible to answer for me because obviously we cannot test, that's not in our interest, test the totality of the non-certified market. We have taken a random sample and it showed 100% were underperforming to varying degrees. If I were to make an estimated or an educated guess, I would say that only certification guarantees performance at the published level, published by the manufacturer. I mean, 48 products out of literally tens of thousands of products is a very small sample. But then again, we had 100% underperforming. So it's quite alarming by as much as 31%, although that was certainly the maximum deviation. So in short, I cannot answer that, but anecdotal evidence suggests that there is underperforming. There's a lot of underperforming products in the market.
I see. Thank you very much.
By the way, not so much on the compressor side. The reason being, one minute. The reason being that compressors, the performance of compressors can very easily be verified. Very easily, you know. Whereas, for instance, if you look at heat rejection equipment or remote cabinets in a supermarket, the actual performance of a single cabinet is impossible to determine in an installation in a supermarket. So
I see.
Anyways, thank you very much for letting me present.
Thank you also for this extra information. And with this, I would like to give the floor to our second speaker of session number 4, who is Mrs. Güneş, Sema Güneş. The title of her presentation will be Comparison of the Environmental Effects of Regenerative and Recuperative Burners. Mrs. Güneş, the floor is yours, please.
Thank you, Mr. Çakan. My name is Sema Güneş. I am working at EcoStar company as an R&D engineering, and I am sharing my screen. Dear youth and college, today presentation we will be examining in environmental effects of regenerative and recuperative burners used in industrial combustion system. In this comparison with conventional process burners, we will focus on their impacts on hydrocarbons and greenhouse gas emissions, and particularly discuss the important finding regarding energy saving and emission reduction. The focus of this research is on reducing emissions and improving energy efficiency in industrial combustion system. As we know, HVAC systems are circular in both energy consumption and emissions, contributing to significant percentage of global carbon dioxide and NOx emissions. HVAC system account for 10 to 50% of carbon dioxide emissions, 30 to 40 of NOx emissions, and carbon dioxide emissions in the energy sector. The need to improve energy efficiency and transition to clean energy sources has never been more important. In our study, we especially looked at three types of burners. Conventional process burners, which although low cost and simple, result in higher level of emissions. Recuperative burners, which can achieve up to 30% energy saving by using heat exchangers to execute heat directly to the combustion air. Regenerative burners, the most efficient option, actually, with potential fuel saving of up to 50%, thanks to their ability to recover 85 to 19% of the heat from exuded gas. Avoided energy in buildings refer to the total energy consumed during the production, transportation, and construction of buildings materials. In this context, HVAC system play a significant role in the energy consumption of buildings and are circular in reducing carbon emissions. Globally, the energy production and industrial sectors are responsible for approximately 70% of carbon emissions. Therefore, there is significant potential to reduce greenhouse gas emissions by focusing on burner technology. Regenerative burners. I have been talking about burner since I started the presentation. What is the burner? The burner turns the fuel into flammable gas and sprays it into a combustion chamber where it burns. And this combustion products heat and energy, and this heat energy is used in a heating system. Regenerative burners, these burners are particularly ideal for high temperature process. This process reduces fuel combustion and increases combustion efficiency. They significantly change energy efficiency and minimize NOx and carbon monoxide emissions by operating in pairs and using ceramic heat regulators for short-term heat store. Regenerative burners can recover 85 to 90% of the heat from furnace exhaust gas. They preheat the combustion air to very high temperatures, potentially reducing fuel consumption by up to 50%. It is used in the steel industry, melting and holding furnaces. This indirectly reduces the carbon footprint of the iron used in buildings and the pollutant emission resulting from its production. Regenerative burners use heat exchanger to transfer the heat from exhaust gas directly to the combustion air. These burners are particularly preferred in medium and low temperature process. They enhance combustion efficiency, reduce fuel consumption, and consequently lower carbon emissions. They use a heat exchanger to recover heat from furnace exhaust gas and preheat the incoming combustion air. This technology can achieve up to 30% energy saving. Despite having a compact design compared to regenerative burners, they offer similar energy efficiency benefit. It uses glass production, ceramic production, and iron and steel production. Conventional process burners are typically low-cost and simple combustion system. These burners exhibit lower performance in terms of energy efficiency. They result in higher level of hydrocarbon and greenhouse gas emissions. The environmental impact of conventional burners is riskier compared to innovative combustion technologies. This process has significant disadvantage in industrial application when considering environmental sustainability. In this table, NCPB natural gas fired conventional process burners, NRCB natural gas fired recuperative burners, NRGB natural gas fired regenerative burners. You can see the fuel flow rates and fuel saving percentage of different burners using natural gas, while conventional process burners do not provide any fuel saving. Recuperative burners achieve a 30% reduction, and regenerative burners offer up to 50% saving. Looking at carbon dioxide and carbon monoxide emissions, it is evident that regenerative burners are the most efficient system in the long term. Our results show that regenerative and recuperative burners provide significant advantage in terms of energy saving and emission reduction. In industries such as cement and steel, these burners contribute to reducing the carbon footprint and exchanging environmental sustainability. Due to their high heat recovery and low fuel combustion, carbon dioxide and carbon monoxide emissions are significantly reduced. Over a 10-year operational period, it has been observed that regenerative burners can reduce carbon monoxide and carbon dioxide emissions by half compared to standard process burners. In conclusion, regenerative and recuperative burners provide a significant advantage in energy saving and emission reduction. As we strive towards a more sustainable future, these technologies will play a vital role in reducing the environmental impact of industrial process. Thank you for listening to me.
Thank you, Mrs. Güneş. We understand from your presentation that the conventional burners should be somehow excluded from the sector, and instead regenerative burners should take their place in order to save, in order to decrease the carbon footprint. Thank you very much once again. We are ahead of our time, but we keep going on with the presentation of Mr. Özer, Mr. Emre Özer. The title of his presentation is Renewal of circulation pumps used in HVAC systems and the effect of pump management functions on energy efficiency. Mr. Özer, the floor is yours, please.
Hi, everyone. I'm going to share my presentation.
Please go ahead.
Okay, it's freezing. Şu an everyone again, welcome. I am Emre Özer from Istanbul. I'm working on automation systems. I am a mechatronic engineer. I am working as a field engineer on energy department. I just graduated last year and it's my first project actually. I hope I can handle it. And I'm going to present you renewal of circulation pumps used in HVAC systems and effect of pump management functions on energy efficiency. First, let's start with summary about the project. First, let's look how did this project came out. In 2022, at the Technopark Istanbul campus, a detailed energy audit was conducted. As a result of this audit, 7 solution options has been selected for reducing the unnecessary energy consumptions, minimizing energy losses, and recovering wasting energy. Also in the audit, utilization of energy efficiency equipment and systems and process improvements are considered. So in this project, we are going to examine 2 of them, these options, and which these are changing replacement of the circulation pumps and upgrading the main utility water booster pump with higher efficiency class. Then if we examine why these options are considered suitable, replacing the circulation pumps with high efficiency motors is generally a recommended and preferred application type due to fast return on investment. As a general approach, estimate that total consumption can be reduced by 20%. In this presentation, we are going to examine data and control techniques, use the efficiency implementation project, and we are going to check can we actually reach these numbers. First part is system inventory, and the first is pumps. Inline type pumps are used, and single stage closed couple voltage pumps are used actually. Also, all pumps has integrated frequency converter. The pumps had top blowout design and discharge parts were identical. These properties are contributed to replacement and gives us better maintenance. The motor efficiency also is classified as IE5, which is the highest efficiency class at this point on the industry. And the next component is control unit. System is controlled by this unit. The control panel works by comparing the received signal with the set point value, and it can be operating the pumps for different ways, like external differential pressure, temperature, or differential temperature. The panel is designed to monitor and control pumps with integrated frequency converter, and it can be also monitor and transmitted to controller these frequency converter values. Additionally, all collected values can be transferred to the building management systems using via Modbus cards. And the final part is the system inventory is pressure booster set. This pressure booster system is supplied as a compact assembly with integrated frequency converter and a control panel. All pumps in the system are speed controlled, and the system adapts to its performance based on demand by cutting in out the required number of pumps and through parallel control of the operating pumps. Pump changeover occurs automatically depending on load, time, or faults. And also this motor efficiency is classified as IE5 energy class. Next headline is implementation methods. And first method is integrated frequency converter status. We are going to examine data and control methods for energy efficiency implementation and management functions. In the previous systems at the area, many pump groups were operating with many motors, but only a single frequency converter were using. By using a separate converter for each motor, each one can be controlled by separately, and thus each motor can enable operate at different loads and speeds according to specific requirements. In this way, the system can be controlled more precise and efficient. As a result, optimized motor performance leads to energy savings and higher system efficiency. Also, with this way, the motors are expected to have a longer lifespan. And the other implementation method is translation of star delta systems to frequency converter systems. In the previous system, some pumps were operating with star delta method. In a star connection, the motor runs at a fixed and lower voltage, while in a delta connection operates at full power. So in this method, motor starts with low power, and after a few seconds, system operates at full power, which is so bad, as you imagine. When we do this transition to frequency converter systems, we can control these motors separately. And frequency converter operation, the motor's speed optimized, leading to energy savings. Furthermore, more precise control and extended lifespan can be obtained with this way. And the other method is more control method. Parabolic control with differential pressure indicator. In this method, the system is controlled by using a differential pressure sensor and a control unit. With parabolic control system operates more efficiently based on actual demand. In this control system, the pressure difference between the inlet and outlet points is continuously measured to determine the system's current need. Then operating speed of the motors dictates. The control curve is not linear, but parabolic and adjusts according to the flow rate demand, what system needs on the time. And this ensures that the system operates at optimal levels. Consequently, consumption is significantly reduced, and in addition to the saving obtained from the efficiency class, 50% of energy savings are projected. And the last control method is temperature differences. In this control method, temperature sensors are placed at the inlet and the outlet points, and the system is operated based on this temperature difference. This method is used for specific pump groups like primary boiler pumps and chiller pumps, which is the systems are temperature-focused systems. This approach ensures that the system is not affected by pressure fluctuations or resulting in more stable control. The temperature difference is used to estimate the load, and the corresponding to flow rate is set via the control unit. So in this system, flow meters were used to get flow rate in this method. The system is then operated by comparing the flow rate value from the flow meter installed on the discharge line with the set value. With the set value, we're operating the system as a temperature difference. And the last part is measurement and verification part. This part is crucial for ensuring the project runs correctly. And the project IPMVP was adopted for this project. And option B is selected as a verification method. In this method, the system must be monitored continuously, and option B makes this the solution. And for this purpose, a flow meter, energy analyzer, and pressure sensors were added to the system. Also to obtain accurate results, consumption values before and after the change must be compared for the same periods. Therefore, the measurement and verification process will take place over 1 year. But for now, we only have a few months of data, so we are going to make some assumptions in our later calculations. And phase 1, in the measurement and verification part, we divided to two phases in the process, because in the first phase, we covers the period before the pump replacements. I mean, this phase basically represents our reference point period. These values will be compared with the post-implementation data and indicating system accuracy for the full year of continuous measurement. Additionally, by the IPMVP rules, before replacement, the electrical consumptions, flow rates, and pressure differences of the pumps measured partial loads, like 100%, 50%, like this. And test data also for these loads have been recorded. And if the verification steps are applied by taking a pump group as an example, we get these values on the table, as you can see. In the table, hourly average power consumption was recorded as almost 32 kilowatts for reference periods. Based on the assumption, as we told before, that this pump group operates for 15 hours annually, the annual consumption is calculated as follows, which is 48,000 almost kilowatt hour. And the next part is phase 2. In the second phase, we got values after the replacement. So you can see hourly consumptions, and it's 21.5 kilowatts. When we do this annual consumption, we are getting 32,000 kilowatt hour annual consumption. However, to issue more accurate results, the necessary approaches will be explored in the next section, because we are not comparing these data on the same time. Because, like just I said, instantaneous or daily recorded values can be misleading for different periods. Therefore, energy consumption must be compared to the load at that time. The load is determined based on the flow rate and varies across different pump groups. And these are our formulas for the do this comparison more accurate. And we are getting 37,000 kilowatt hour for annual consumption. And when we do the calculations, we are getting almost 11,000 kilowatt hour annually energy savings, which is as a 22.8% energy savings. And finally, in the conclusion, in this project, our goal was the replacement of circulation pumps and get 20% to 30% energy savings. And after replacements and using of control methods, we got, like before I said, 22.8% energy savings. This represents a significant gain in terms of environmental sustainability and a reduction in energy costs. Moreover, the continuous monitoring and verifications of the implemented changes have ensured that the project met its goals. In conclusion, the replacements of circulation pumps with more efficient motors has not only provided energy savings, but also improved the system efficiency and reliability, presenting a successful solution, as we can say. That's all. Thank you for listening.
Thank you very much, Emre, Özer. I wonder, this is just a testing case you presented, right? I mean, what would be your estimation or anticipation about the payback period of such a system when it's established? I mean, what would be the payback time? You can give an average value, of course.
Our reference period is a month.
Uh-huh.
We take the values for a month and we compare this another month after the replacement. We compare these both months, but we couldn't compare this significant numbers because the periods are not the same.
Yes, I understand. Yes.
Yeah. So we did some assumptions, and after the assumptions, we get 22.8% energy savings. Actually, if we didn't met these calculations, we were getting more energy savings. As you can see in the phase 2 after the replacement, we are lowering the power consumption on 21 kilowatts, but in the verification part, after our calculations and load-based approach, we are getting power consumption to almost 25 kilowatts per hour. So actually, we can't compare these for same time, so we have to do this load approach, and after this we are getting, like before I said, 22.8% energy savings.
Energy savings, okay.
Yes.
Well, thank you very much for your efforts and time. We are ahead of time, about 15 minutes, plus another 15 minutes before the session. The next session starts. We have about half an hour. We expect you to be with us in session 5, and see you then. Bye-bye.
See you.